Hello everyone, today we are going to talk about deep learning, a comprehensive overview. Deep learning is a subfield of machine learning, has revolutionized various industries by enabling computers to learn from data in a way that mimics human intelligence. This field utilizes artificial neural networks with multiple layers to extract intricate patterns and features from complex data, leading to breakthroughs in areas like image recognition, natural language processing, and autonomous driving. Introduction to deep learning is a subfield of machine learning, employs artificial neural networks with multiple layers to extract intricate patterns and features from complex data. These networks are inspired by the structure and function of the human brain, allowing computers to learn from data in a way that mimics human intelligence. Key concepts: deep learning leverages algorithms that learn from data through a hierarchical process, gradually extracting higher level features from raw input. These algorithms are capable of learning representations of data that are more complex than traditional machine learning methods. Neural networks. Artificial neural networks are interconnected nodes inspired by the structure of the human brain that process information and learn patterns. These networks consist of multiple layers, with each layer extracting increasingly abstract features from the data. Applications. Deep learning has found applications in a wide range of domains, including image recognition, natural language processing, speed recognition, autonomous driving, and medical diagnosis. Advantages. Deep learning offers several advantages, including its ability to learn complex representations from large amounts of data, its flexibility in handling diverse data types, and its ability to achieve high accuracy on challenging tasks. Overview of deep learning architectures. Deep learning architectures are designed to address specific tasks and data types. Each architecture has its unique strengths and weaknesses, making them suitable for different applications. Feed-forward neural networks process information in one direction from input to output without feedback loops. They are commonly used for tasks like image classification and regression. Convolutional neural networks are also called as CNNs. They are specifically designed for processing spatial data such as images and videos. They utilize convolutional filters to extract features and learn patterns from the data. Recurrent neural networks are designed to handle sequential data such as text and time series. They have internal memory that allows them to process data in order and consider previous inputs. Generative adversarial network consists of two competing neural networks, a generator and a discriminator, that work together to generate new data that resembles real data. Convolutional neural networks are specialized deep learning architectures designed for processing spatial data, particularly images. They excel in tasks like image classification, object detection, and image segmentation. Key features: CNNs employ convolutional filters to extract features from images by sliding these filters across the input data. They also utilize pooling layers to reduce the dimensionality the feature maps, making the neural network more efficient. Architecture: CNNs consist of multiple layers, including convolutional layers, pooling layers, and fully connected layers. These layers work together to extract increasingly complex features from the input data. Applications: CNNs have revolutionized fields like medical imaging and autonomous driving and security systems. They are used for tasks such as disease detection and object recognition and facial recognition. Recurrent neural networks and long-term memories are a type of neural network specifically designed to handle sequential data such as text, speech, and time series data. They possess an internal memory that allows them to process data in order considering previous inputs. RNN architecture have recurrence connections that allow information to flow through the network over time. They can be trained to predict the next element in a sequence or to classify sequences based on their patterns. LTMs are specialized type of RNN that address the vanishing gradient problem, a common issue in RNNs that prevents them from learning long-term dependencies in data. LTMs have a more complex internal structure that enables them to retain information over longer periods. RNNs and LTMs are widely used in natural language processing, speech recognition, machine translation, and time series analysis. Generative adversarial networks are a class of deep learning models that are capable of generating new data that resembles real data. They consist of two competing neural networks, a generator and a discriminator. The generator works takes random noise as input and generates new data that attempts to mimic the distribution of the real data. Discriminator. Discriminator receives both real and generated data as input and tries to distinguish between them. It outputs a probability that the input is real or fake. Training. During training, the generator network learns to generate data that fools the discriminator, and the discriminator network learns to better distinguish between real and fake data. Challenges in deep learning. While deep learning has achieved remarkable success, it also presents several challenges that researchers and practitioners need to address during to further advance the field. Challenge: data scarcity and imbalance. Description: the deep learning models require a large amount of data for training. Limited data availability and imbalanced datasets can lead to poor model performance. Model interpretability, model interpretability and explainability. Data learning models can be complex and difficult to understand. Lack of interpretability and explainability can hinder trust and adoption of these models. Computational complexity and hardware limitations. Training and deploying deep learning models can be computationally expensive and requires significant hardware resources. Ethical considerations. As deep learning models become more powerful, ethical considerations surrounding bias, fairness, and privacy need to be addressed. Data scarcity and imbalance. One of the most significant challenges in deep learning is the need for large amount of data for training. Limited data availability can lead to poor model performance, especially in domains with specialized or niche data. Data augmentation can artificially increase the size of the training datasets by creating variations of existing data, such as rotating or flipping images. Transfer learning involves using a pre-trained model uh, trained on a large data as a starting point for a new task, leveraging knowledge gained from the previous task. Active learning strategies allow the model to select the most informative data points to label, improving the model's performance with fewer labeled data. Synthetic data generation techniques create artificial data that resembles the real data, expanding the training dataset without relying on real-world data. Model interpretability and explainability. Deep learning of models often lack interpretability, making it difficult to understand how they reach their predictions. This lack of transparency can hinder trust and adoption of these models, particularly in critical domains like healthcare and finance. Feature importance techniques like feature importance analysis help identify the features that contribute most of the model's predictions, providing insights into the model's decision-making process. Visualization techniques, visualizing the model's internal representations and activations can provide a better understanding of how the model processes information. Explainable AI focuses on developing techniques to make deep learning models more transparent and interpretable, allowing users to understand the reasons behind the model's predictions. Rule extractions techniques to aim extract human understandable rules the deep learning models, making them more interpretable and providing insights into the model's logic. Computational complexity and hardware limitations. Training and deploying deep learning models can be computationally expensive, requiring significant hardware resources, such as power, GPUs, and specialized hardware. This can limit the accessibility of deep learning for smaller organizations or researchers with limited resources. Cloud computing platforms provide access to high-performance computing resources, allowing users to train and deploy deep learning models without significant upfront investment in hardware. Hardware optimization, specialized hardware such as GPUs and TPUs, are designed to accelerate deep learning computations, enabling faster and inference. Model compression. Deep compression model compression techniques use the size and complexity of deep learning models, making them more efficient and easier to deploy on resource-constrained devices. Researchers are developing more efficient algorithms that reduce the computational complexity of deep learning models, making them more accessible to a wider range of users. That is it. Thank you.